Okay, welcome back Physics 20s to our next lesson in chapter 4. This is 4.2 and we're going to be looking at gravitational force. Okay, so in the last lesson we looked at gravitational field strength and we had the formula G is equal to capital G ms over r squared. And we had a diagram like this where we had a mass in the center. So we said that gravitational field strength, which is this G, and that's measured in meters per second squared because it makes objects accelerate towards that mass, is dependent upon first the mass. So if we have a bigger mass here, which I'm going to shade in green, if that mass is bigger, it's going to have a stronger gravitational field strength. So something would accelerate it towards it faster if that mass is higher. And the other part was the radius. Now this is inversely proportional, that if the radius increases, the gravitational field strength is going to decrease. So switch to red here. I'm going to draw these circles here. If I drop something from, there's ms. If I drop something from this height, or if I hold something up at this height, the gravitational field strength here is probably going to be pretty small because it's a far distance away from the mass. Now, if I go a little bit closer, the G is going to be a little bit bigger. And that's because here, this is a large radius from the center of the mass source to the center of the test mass. That's a big radius. But from here, the radius is smaller. And then if I was going to go one closer, let's draw this one over here, the radius is even smaller. I do want to clarify that it's not like I drop it from this point up here and it's going to have the same acceleration all the way down. It's going to increase as it gets closer and closer because now the radius is getting smaller and smaller. So it's going to be accelerating at a low level up here, but as it falls, it's going to accelerate more. And as it falls, it's going to accelerate more. So the acceleration goes up as the radius goes down and gets closer to that mass source. And this variable r has an even bigger effect on this equation than m did because r is going to be squared. So if we double the radius and go double that distance away from the center of the mass source, that's double and then squared. So this will actually have an effect of 4 because that number, again, radius is squared. So it has a big effect on the gravitational field strength. Now we're going to look at gravitational force. So we know that if we take these two objects, a tennis ball and a bowling ball, the gravitational field strength says that they're going to accelerate towards the mass source of the Earth at an acceleration of 9.81 meters per second squared. And we saw this in the first unit that everything will accelerate like this. But now let's look at the force that is acting on these objects. And we know how to calculate this. We just take F is equal to ma, our force is mass times acceleration. So I'm gonna do that in green for the tennis ball and in blue for the bowling ball. So now I just plug in my values, 0.06 kilograms for the tennis ball, 20 kilograms for the bowling ball, and I get two different numbers. The force of gravity on the tennis ball is only 0.59 newtons, where on the bowling ball, it's 196. So what this shows us is that the gravitational field strength that was only dependent on the mass source, or the mass of the Earth in this case, that's what made the 9.81, the force on that mass being pulled, like the force of gravity on that mass that is being pulled towards the mass source, is dependent on the mass of that test mass. So what I mean there is like the bowling ball, how much force that is going to feel is going to be dependent on how massive the bowling ball is. So the big thing we have to remember is when we're looking at the force of gravity, not the field strength, but the force, this is dependent on both masses. So let's see what this looks like when we calculate it. Before we had Fg is equal to mass times gravity. We were just able to plug in like that. But that was always assuming that G was equal to 9.81 because we were always talking about the surface of Earth. But now we're going to have examples where masses could be way above the surface of the Earth, or it could be talking about different planetary objects like moons or other planets going around each other, which is not going to be on the surface of the Earth. So now we're going to have to use our formula for field strength to figure out what that G is equal to. And the formula for that was G is equal to capital G ms over r squared. So now I'm just going to plug that in. And all that means is I have to take this formula multiplied by the mass. So I'm going to write that now as our new formula for Fg is Fg is equal to, I'm going to put the field strength actually first, Gm over r squared. Now again, just multiplied by this other mass should give us force. So I just have to plug another m in there. Now it's important, those are not the same m. We talked about the other one with the bowling ball. The bowling ball was one mass and the Earth was the other mass. The two masses that are pulling a force towards each other, both of those masses are important. So I'm just going to put m1 and m2. And you might be thinking, well, which one's the mass source? Well, if I look at this example where I have this ball here, we would normally call like the Earth the mass source of the gravitational field. But all masses have a gravitational field, but now we know that for force, both of these masses, this one here of the object being dropped and the one of the Earth, are both important. And this means that both actually contribute to the force of gravity, which means that if we have the force of gravity being pulled on the ball, that is going to be the 196 newtons that we saw from before. But if we were to calculate the force that the ball, that bowling ball, had on the Earth, it's actually going to be the same value. So switch to red here. It would actually be pulling the Earth towards it at 196 newtons. Now, it doesn't really seem to make sense how the bowling ball, a small mass, would have that same effect on the Earth. But if we take our equation, because these masses are the two things that are pulling on each other, it doesn't change if we're calculating the Earth's pull on the bowling ball or the bowling ball's pull on the Earth. It's the exact same equation. Now, the reason why it's not going to be as dramatic effect is because when we go F is equal to ma, if this is 196 newtons and we divide that by the mass of Earth, that is going to be a very small acceleration. So when that force of 196 newtons is applied to both the ball and the Earth, and they're coming together, it's an attractive force between the two. The Earth is not going to move very much, but the ball is going to accelerate significantly. And so to sum up gravity, or the force of gravity, is to say that it is a force that acts between any two masses. Both masses are important, and it increases with the value of each mass, saying if I increase this mass, Fg goes up. If I increase this mass, Fg goes up. And that is going to decrease with the square of the radius. So as the radius goes up, force of gravity will go down a lot because that radius is squared. So let's take a look at some examples that says, what is the force of gravity that the sun exerts on the Earth? Okay, again, not too hard to plug these in. We know the formula Fg is equal to Gm1 m2 over r squared. It's mostly just handling these big numbers in your calculator, but let's write all these in. So G is 6.67 times 10 to the negative 11. Mass, there's two masses, and this is between the sun and the Earth. The Earth is 5.97 times 10 to the 24 kilograms, and the sun is much, much bigger. It's 1.99 times 10 to the 30 kilograms. And all this data is on your formula sheet. And then we're going to divide by the radius. So we need to find the radius from the center of the Earth to the center of the sun. That's going to be the Earth's orbital radius, which is 1.5 times 10 to the 11 meters squared. So putting this all in our calculator, I put brackets, 6.67 times 10 to the negative 11. Close our brackets, put 5.97 times 10 to the 24. That's going to be Earth. And brackets 1.99 times 10 to the 30, which is going to be the sun. That's my numerator value. It's really big, and I just have to divide by the distance from the center of the Earth to the center of the sun, which is 1.5 times 10 to the 11, and square that number. Oh, I forgot a bracket. Make sure you don't forget that. Bracket 1.5 times 10 to the 11 squared. And I get an answer of 3.52 times 10 to the 22. And that answer is going to be in newtons. Now the next one says, what is the force of gravity that the Earth exerts on the sun? Now this seems like it's a different question, but if I'm going to put Fg is equal to Gm1 m2 over r squared, again, the distance between the Earth and the sun is the same. The masses that I'm going to put in are the Earth and the sun, which are the same, and G is also the same. So this should give me my exact same number of 3.52 times 10 to the 22 newtons. Now we'll be acting in the opposite direction. So one should probably be positive and one should be negative. Because again, when we have a mass here and a mass here, they're going to attract each other. It's attractive force of gravity between two masses, and these arrows are pointing in opposite directions. So we should probably make one plus and one minus. And our last example here says, what is the weight of a 10 kilogram mass at the top of Mount Everest? Okay, so first when it asks for weight, we know that it's asking for the force of gravity. Now, normally when we're talking about on Earth, we go times 9.81. But what this is trying to get at is say we are moved significantly further away from the center of Earth than if you're just dropping something on the surface. So we want to see if the weight is going to be any different there than it would be on the surface. Just for curiosity, on the surface of the Earth, we would go Fg is equal to mg, and we go 10 kilograms times 9.81 meters per second squared. We get 98.1 newtons for the force. You could call it negative if you want to call negative down too, but there's a force of 98.1. So now we're saying up here, there's a person holding on to this ball. The ball is stationary. How much weight is going to be acting on that ball? So now we have to use, it might not be 9.81. We're expecting it's going to be a little bit less because the radius is a little bit higher. So Fg is equal to G m1 m2 over r squared. G is 6.67 times 10 to the negative 11. The mass is the mass of Earth and the 10 kilograms. So it doesn't matter which order you put them in. I'm going to put 10 kilograms first, 5.97 times 10 to the 24 next. And now divide by the radius. Now this is a little bit tricky. We need to find the center of Earth to the center of this ball. So how we do that, if this is the Earth, this is not going to be to scale drawing, but if I'm measuring usually from the center of the Earth to dropping it on the surface, it would be the equatorial radius. But now we need to go up a little bit higher. So we need to add that extra height above the surface of the Earth. So the equatorial radius of Earth is 6.37 times 10 to the 6 meters, but now I have to add this additional height above the surface of the Earth. And that is going to be, it said in the question, 8,850 meters. And square that number. So here in the calculator, we have 6.67 times 10 to the negative 11, times that by 10 kilograms, times that by 5.97 times 10 to the 24. And I hit enter to get my number for the numerator. Then I'm going to divide by, this is kind of trickier here. I'm going to need to use a lot of brackets. So I need that whole number to be squared, so outside of brackets, but then I want to keep my two numbers that I'm adding with brackets on the inside. So I'm going to hit bracket twice and put 6.37 times 10 to the 6. That's the equatorial radius. Close that bracket. I'm going to add 8,850. And now I'm going to put end bracket saying that whole sum is going to be squared. And I get a number of 97.86. So 97.86. To 3 digits, that would round to 97.9 newtons. And so it is slightly less weight than it would be if you're on the surface of Earth. So as we're getting further away from the center of Earth, we get a little bit less force of gravity. Not so significant with the height of a mountain, but again, as you could think if you went to a satellite or if you went to an asteroid or went to the moon or something like that, we're getting a lot further away and the force of gravity is getting less and less. So I hope that made sense for you. Make sure you give the practice questions a try and I will see you in the next video.